Great. I've just got the recording in process information. Thank you very much, Marco, for the invitation to speak at this seminar. It's a pleasure to be here. So I'm going to talk about a topic that I know that some of you in the audience have heard me speak about before, though I'm sure not everyone has heard me speak about this before. It's a more of an additive combinatorial topic than an analytic topic, but I talked to Marco before and he suggested that this would be still suitable for the audience of this seminar. It's a project that I've been working on for nearly 3 years now in various collaborations, and we've written a couple of papers about it, and for better or worse, there are still some new things to find out. So one of the things I want to do in this talk is, of course, mention what we've been working on for the last few years, but then give you some update of a few new results, unpublished results, which we now know how to prove and which improve upon some of our earlier work. So this is the plan for the next 50 minutes or so. It's a 5-part talk, albeit all the parts are quite short. So of course, I want to give you the setup for the problem and describe a few simple examples and motivate the study of what we're going to do. We'll be dealing with finite subsets of Z to the D, and although the richest theory happens for general D, and D in particular at least 2, the motivating issues can be seen in dimension 1. And so I will discuss this, and this is a more familiar setting for lots of the additive number theory we do. So that will be the second part in dimension 1, and then I'll generalize some of those notions to dimension D in the third part of the talk. There will be 2 notions of stability that will become evident throughout the talk, one involving the structure of a set of integers, or more generally, a set of lattice points, and one involving simply the size of the set of integers or a set of lattice points. And these will be somewhat distinct, both in terms of the statements and in terms of the methods involved, so that the final couple of sections of the talk will be discussing these 2 things in turn. Okay, so this is a specialist seminar, albeit not a specialist additive combinatoric seminar. So I will begin by a few basic definitions. And of course, I should say that this work is the product of joint work in various collaborations, some just with Andrew Granville and some joint with Andrew Granville and George Shakan. Okay. So what's a sumset? Throughout, we'll have A being a finite subset of Z to the D. And to remind you, the sumset is literally the set of all sums from the set A. So the single sumset A plus A is just the set of all sums A1 plus A2, where A1 and A2 come from the set A. But in this talk particularly, we'll be interested in iterating this construction. So more usually, we'll be interested in the n-fold iterated sumset, where we take n summands, A1, A2, so on up to AN, where all these AI lie in the set A. I should just stress, and I hope you can see my cursor moving here. Marco, is my cursor visible? Yeah, good.
Yes, yes.
So later on, there'll be some pictures that I'll want to gesticulate over using my cursor. I want to stress that these summands could repeat. We're not dealing with distinct summands here. A1 is allowed to equal B2. Okay, so these are no doubt very familiar definitions. At this juncture, I want to introduce one piece of notation that will come up repeatedly in this talk. It's the following. So, rather natural notation, for a set of integers or integer lattice points A, will denote B minus A for, well, the set of all differences, where B is some fixed integer or some fixed lattice point. B minus A is the set of all differences. Okay, so this seemed the best place to give this notation, which is why I did it here. Now, if A was a subset not of Z to the D, but of some finite group, and we repeatedly iterated this construction, took the n-fold sumset for some very large n, then eventually you'd go away and you'd generate, well, either a subgroup of the finite group or a coset of a finite subgroup. And so this is maybe not so interesting, but when A is a subset of a torsion-free abelian group, more complicated things can happen. So this is the motivating question. What stability properties can you obtain for the sumset NA when n gets extremely large? This is a slightly opposite point of view to what we often do in additive combinatorics, where we're interested in the structure of A plus A. And maybe if A plus A is small, what does it say about A? This is the setting of Feynman's theorem. This is something that you know about. That's not the focus for this topic. Okay, let's have an easy example, almost embarrassingly easy, but in which the main phenomena that we'll study in greater generality are nonetheless visible. So D equals 1 dimension, and the set A will just have 3 elements, 0, 3, 5. So you go away and calculate that the sumset A plus A has size 6, it's these 6 elements. The threefold sumset has size 10, it's these 10 elements. And in fact, once you kind of spot what's going on here, you sort of see that there's an interval in the middle, in this case between 8 and 11, in which all elements are represented, 8, 9, 10, 11. But there are a few gaps near the beginning and near the end. So at the end, we're missing 14 and 12. And at the beginning, we're missing 1, 2, 4, and 7. Okay, so this is some embarrassing schoolboy arithmetic exercise, but it will generalize in a way that's less obvious. So once you've seen this, you can actually just prove by induction that this structure always holds. So it looks a bit of a mess when you write it down, but this is very straightforward. The n-fold iterated sumset is always, well, it's between 0 and 5 times n. 0 is the minimum element you get. 5 times n is the maximum element you can ever get. Add 5 every single time, you'll get 5n. But you'll never get 1, 2, 4, or 7. And furthermore, you will never get 5n minus 1 or 5n minus 3. So in this case, that was 14 and 12. Those elements you will never find in the iterated sumset n. Okay, it's not so hard, and just by induction, you can prove this holds for all n. Okay, so this is a sort of structural stability. We've written down a precise form of the sumset, and it's a whole interval, an approximate group, if this is a language that you like, without certain fixed exceptional sets. Now, the set 1, 2, 4, 7 is independent of n. The set 1, 3 is independent of n. So we'll define this formally later on, but this is the kind of structural stability we'll be studying. So that's structure. What about size? Well, when n is large enough so that these two exceptional sets are disjoint, we can just read off the size of the sumset. Namely, it's going to be the length of this interval minus 4 minus 2. Now you're removing these two different sets. Okay, let me just write that down in a different way. The size of the sumset is going to be the length of the interval, 5n plus 1, that's the number of integers, minus the number of exceptional elements, provided that these exceptional sets are disjoint, right? And that only happens when n is at least 3. When n is 2, you get an overlap between these two sets. When n is at least 3, they're separated enough, so you can just read off this formula. And in a way that might seem a bit obtuse for now, I'm going to write this as a linear polynomial in n. Okay, this is some fixed polynomial depending on my set A, and it's a linear function of n, but in future slides this will be a polynomial. So what we've shown is that the size of the sumset agrees with this polynomial, not for all n, but at least when n is at least 3. This is an outcome of our investigation on this slide. Okay, so what we're going to try and do, and indeed there is a literature on this problem, is to look to generalize both of these features to a general subset A and maybe to general D. All right, so before I move on, are there any questions at this juncture? Okay, seeing none, I will go on, but if I'm going too fast or saying something stupid, I'm sure that will happen. Please shout out, or else it's very hard to know on these online seminars whether anyone's following. Okay, so generalizations. Let's think about the structure of generalization. So this was worked out a long time ago, over 50 years ago, by Mel Nathanson. So it's still in dimension 1, but it's for a general set A. So what did he do? So A is a subset of the integers, and by translation dilation, we can assume that its minimum element is 0, and its maximum element is, well, something positive. Let's call it B. And the GCD of all the elements is 1. Of course, if all the elements of A were even, we're only going to represent even things, and this is somehow not an interesting dynamic. So we divide out by any common divisors until the GCD is 1. Now, Nathanson showed that the structure that we had in the example holds all the time. So there exist two finite sets, C and C primed, such that, well, for large enough n, and we'll come to that, the iterated sumset has exactly the structure I claimed. It's the whole interval between 0 and b times n, without an exceptional set near the beginning, that's C, and without an exceptional set near the end of that interval, that's bn minus C prime. That's exactly the same image as we had before. And he showed that that holds eventually. And in particular, he got an explicit bound. He said that it holds as long as n is at least b squared times the size of a minus 1. Okay, we'll come back to this later on, but one can perhaps immediately see a few things one would like to know further than what Nathanson proved. But that's the classical result. That's structure. What about size? So this was handled in the early 90s in what I still feel is a very surprising result by Khovanskii. So this is about general D. So A is a finite subset of Z to the D. Khovanskii showed that there exists some fixed polynomial, depending on the set A, with rational coefficients, and degree at most D. So when D is 1, that just means the linear polynomial we had before, but in general, degree at most D. And some threshold, which for the purposes of this talk, we'll call the Khovanskii threshold, such that the size of the iterated sumset agrees exactly with this polynomial once n exceeds this threshold. So this is what I might mean by size stability. There is an extremely structured formula for the size of this iterated sumset, which doesn't hold all the time, but it holds eventually.
Alej, I have a question. Those the sets C and C prime, they can be explicitly computed or just exist the sets?
Just that they exist. It's a complicated question, and in general, an NP hard question to compute what these exceptional sets C are. People who think deeply about the Frobenius postage stamp problem know a few things, but even for sets of 5 elements, I believe it's not known how to computationally efficiently establish C for sets even of size 5.
And just another question, perhaps a silly question. If A is the set of primes below some x, and this somehow recovers the question of Goldbach or etc. or no?
No, so the issue, it's a slightly different question, because so if we think about, let's say, Vinogradov's 3 primes theorem, or even Schnirelmann's theorem that the primes are an additive basis of some finite amount, every odd number is the sum of whatever he got, 30,001 primes, that's still some fixed n. And so we're not making any claims about the set A being an additive basis of finite type or whatever. This yeah, so in particular, note that this threshold n for n that we're considering, it depends on the set A.
Yes, I forgot to read this last line. I am just thinking for small n and see what happens. Or okay.
No, it's a good question, and indeed, it's kind of how we normally think in these additive problems. We're thinking about some finite number of summands, but the focus is different in these kind of questions.
Okay, thank you.
Okay, please shout out if you have any other questions. So these are the two classical generalizations, but you see that there are lots of gaps that are not kind of known. So here are three aims that you might try and find out, and they're what I'll discuss for my remaining time. So Nathanson doesn't claim that this bound is tight. So can you improve it? And maybe the dream would be to improve it to such an extent that you could exactly identify the extremal examples. So you have a bound which holds and is tight in the sense that you can identify exactly the examples for which the bound is optimal. That might be something you'd want. Now, Khovanskii's result is this delicious higher dimensional thing involving polynomials of degree d, whereas Nathanson's result just stays in the world of one dimension. So what's the higher dimensional analog of Nathanson's theorem? What does higher dimensional structural stability look like? And can you prove it? It's another thing you might want. And also note the discrepancy here, that Nathanson had this nice explicit bound, and I've just proved an existence statement here. I've just stated that there exists some threshold, and this is not by accident. Khovanskii's original proof is a cunning reduction of the problem to a theorem in commutative algebra, of which more later. There were some combinatorial proofs by Nathanson and Ruzsa about 10 years later in the early 2000s, but also ineffective. That don't give any explicit bound for what properties of A you should look for to determine this threshold. And there are a couple of very special cases in which the threshold was known a couple of years ago, but no general results at all. So that's another direction that you might push these classical results. So I'll talk about all three of these in the next half an hour. Okay, so
I have a question. Oh, sorry.
Oh yeah, I'll go back. Yes.
Yeah. So this is about the support of convolutions. Is this related with central limit, like a quantitative estimates for central limit theorem?
It's a good question. It's not an angle that we've pushed very hard. I think that depends exactly how you phrase it, but the most applications of the central limit theorem that I would know or care about are for, well, if not necessarily finitely supported random variables, then random variables that are concentrated around some set and some tail. Yeah, I think I'm not going to be able to give you a sensible answer. Okay. I think it's not something that we've thought about too much.
I think this Nathanson theorem is just the same if you have a weighted distribution over the integers, I guess, like a positive weight. So you get the same support when you iterate convolutions of these measures. But my question would be...
So it's a statement about the support, but not necessarily about the distribution you get on the support. I mean, there are versions of this for so-called sort of T-popular sums for not just the support, but the support of numbers that can be represented at least T times in this sumset, which is slightly more along this kind of convolution, sort of level sets of convolutions that you might think about. But that wasn't what we focused on in these projects. Okay. So let me talk a bit more about dimension 1. Most of the richer mathematics comes in dimension D. But let's focus on these exceptional sets a bit more, going back to Marco's question. So back to our simple example, A being the set 0, 3, 5. And let me bring another set into discussion, which it turns out will be heavily related. This set 5 minus A. So it's almost A flipped around 0 and 5. You get 0, 2, 5. Now, we're taking sums of elements of A, so of course the semigroup generated by A is relevant. So let's have a notation for that. Oh, this is the structure that we had before. Here's my notation for the semigroup generated by A, and of course, because 0 is contained in A, it's just the nested union of all the n-fold sumsets. Now, this is the late 19th century schoolboy problem that's sometimes known as the Frobenius postage stamp problem, to prove that if you had unlimited stamps of 3 cents or 5 cents, then you could sum to any positive cost of stamps except 1, 2, 4, or 7. So this set 1, 2, 4, and 7 is exactly the gaps of this numerical semigroup, or you could call it an exceptional set. So I'll call it E of A. These are the elements of the non-negative integers that cannot be represented no matter how many summands you take. So of course they're not an iterated sumset. But what's going on with 1 and 3? Well, 1, 3 is the gaps for a different numerical semigroup, namely the one generated by 5 minus A. Okay, so what's going on here? If I have unlimited numbers of 2s and 5s, I can sum to any non-negative integer with the exception of 1 and 3. Why can't these elements ever be in the iterated sumset? Well, it's because of this fun identity, that if I take the sumset NA and then flip it around its maximum element Bn, that's also a sumset. That's the n-fold iterated sumset of B minus A. So in this case, 5 minus A. And therefore, in particular, must be a subset of the semigroup generated by B minus A. Okay, so there's nothing deep going on here. It's just a rebracketing, essentially. If I take an n-fold sum, subtract that from Bn, I can rebracket that as the sum of n things of the form B minus A. So this is the sort of deeper justification for why 5n minus 1 and 5n minus 3 can never possibly be in your sumset. What this argument tells you is that in general, okay, so I'm going back to Nathanson's generalization, if I have a subset of Z, minimum element 0, maximum element B, GCD of A being 1, for all n, the sumset is a subset of the interval from 0 to Bn, and you never get the gaps from its own numerical semigroup, nor do you get the translated exceptional set from the semigroup of B minus A. So this looks like a complete horror when you write it down on a slide. This will be the nastiest expression that will appear in the talk. You'll be glad to know. But it's just a generalization of this phenomenon that is a schoolboy exercise from the 19th century. So I'm going to repeat this on the next slide. So this is going to return here. That's the same statement there. So structural stability means that we get equality here. It means that the sumset has expanded and expanded until it fills out the maximum possible set. So the structural threshold is the minimal end such that equality holds in this expression. And it's a fun exercise, if you get bored or confused by anything else that I say, or say incorrectly, to show that when the size of the set A is 3, as in our previous example, actually the structural threshold is 1. So that was what was going on with this special example of 0, 3, 5. Because it contained only 3 elements, equality held all the time in this expression. But that doesn't always hold. So let me give you an example with 4 elements. This is a 4-element set, 0, 1, B minus 1, and B. There are no exceptional sets here, right? The semigroup generated by A is the whole of the non-negative integers. It's got 1 in it. You can represent everything eventually. Similarly, B minus A contains 1. So the semigroup generated by B minus A is also everything. It's the whole of the non-negative integers. And yet, if I want to represent B minus 2, I have to take b minus 2 summands of A to get there. And so this structural formula will only hold with equality when n is at least b minus 2. Because otherwise there's this hole at b minus 2 that you don't get to. Okay, so at least this notion is non-trivial. And to come back to Nathanson's example, in this language, Nathanson's theorem says that the structural threshold is at most b squared times the size of A minus 1. Okay, so this is just converting the theorem I stated into this language. Okay, so now let me mention some results, albeit, as I said, this is at the start of the program, so these results are a couple of years old by now. What Andrew and I proved was large improvements to Nathanson's bound. We show that the structural threshold was actually at most b minus the size of A plus 1. Okay, now you can see there's space for the rest of the statement of the theorem here, so there's something to come. When the size of A is 4, so this says that the structural threshold is at most b minus 3. But I'm supposed to have convinced you up here that this threshold was b minus 2, so this would seem to contradict the statement of this theorem I'm going to try and state. Well, here's the rest of the statement. This bound holds unless A is of this type, or of this type, or b minus A is of one of those two types, for some A between 2 and b minus 2. So the example I showed you was actually quite special. The example I showed you was of this form. And these are the extremal examples. These are the examples that have the structural threshold as large as it possibly could be at b minus the size of A plus 2. And all other examples have the structural threshold at most b minus the size of A plus 1. Okay, so we've achieved this first aim I mentioned. We've got a version of Nathanson's results, which is not only an improvement, but in fact a tight result, and we can identify the extremal families of sets. Okay, so this theorem is going to repeat on the next slide. That's the same theorem. So this improved on some other work. So I said it improved on Nathanson's bound. There was another bound from about 10 years ago, which had size roughly about b squared. And then Andrew and George, about a year prior, had got the first linear bound in B. I see something in the chat. Oh, okay, no problem. Okay, so this was an improvement on a long series of things and the first tight results. I should mention that the story hasn't stopped. So since we proved our results, Lev developed our methods and more. And he showed that, in fact, the structural threshold is at most b minus not the size of A, but 3/2 times the size of A under some conditions. So he needed the set A to be large enough. And also he had to exclude, well, these exceptional families and many more exceptional families. So I'm not going to state the full result because it's quite complicated, but this is the shape of his refinement of the bounds. Okay, in the rest of this slide, I will mention extremely briefly elements of the proof, because in higher dimensions, these methods don't work. And so I need to explain what they are in order to contrast the picture with higher dimensions later on. So what's the idea? Okay. Standard ideas in the field that you should focus on arithmetic progressions modulo B, so modulo the maximum element of A. And so we're looking at elements congruent to C modulo B that are in the semigroup generated by A. Look at the minimum such element and try and understand it. You know, it's a sum of elements of A. How many summands do you require? So this is some minimal representation. We can write this element as a sum of elements of A, where capital N is picked minimally. Okay, and it turns out, and I won't really describe how, that if you get a bound on capital N for this problem, you can convert it into bounds on this structural threshold. So the new game is bound in capital N. Now, there are a couple of completely elementary observations you can make about this setup. Here's one. There's no subsum that's congruent to 0 modulo b. Okay, why not? Well, if there were, we could just remove this subsum, and then we're left with an element that's congruent to c modulo b. It's in the semigroup generated by A, but it's smaller than NCA. So that contradicts this minimality. Okay. But even further than that, for all elements A and A, there's no non-trivial subsum that's congruent to A modulo B. Why? Well, if there were, we could replace that sum by A plus a whole lot of B's. That's a contradiction to the minimality of this capital N. It allows you to get a shorter representation of NC. Now, these are criterion that, Adler combinatorics is perfectly well equipped to deal with. So upper bound N based on these things. It's, of course, very related to bounding the Davenport constant of the group Z mod BZ. That's a thing that you care about. So doing so, we can control N using these two observations. And there's some other Adler combinatorics on the side. We had to use a rather simple application of Knaser's theorem to understand the growth of these sumsets modulo B. But it's not that complicated an application, and indeed our paper is pretty short for this. But that's the ultimate idea. You remove subsums congruent to 0 modulo B until you can't anymore. It works really well in dimension 1, and it won't work for higher dimension. Okay, so I'm nearly finished with the discussion of dimension 1, but I want to mention one scary thing with an open problem. So this is something, again, that I would encourage you to think about if you're interested in these sort of questions. Morally, I hope I've convinced you that the structural threshold seems like it should be less than the Khovanskii threshold. Okay, because of what I said, you keep iterating until N is large enough for that structural formula to hold, but maybe those exceptional sets intersect. So then you iterate a bit more until N is large enough for those exceptional sets to be disjoint. And then you can read off the size as a linear polynomial, I guess, when D equals 1. So that's what I've been putting across to you. And for a long time, we thought this was true, formally, and we conjectured it to ourselves, tried to prove it. The problem is it's false. However, so here's an innocuous looking example of a set with 6 elements. You can calculate the gaps in the semigroup. You can form everything from sums of A except 1, 2, 4, 5, 8, and 11. You can form everything from sums of the set 12 minus A except the element 1. And so what does this mean? You can read off the Khovanskii polynomial from this. It's 12n minus 6. 12 coming from the maximum element minus 0. 6 coming from the sum of these two exceptional sets and size minus 1. But actually, when you do the calculation, the size of the iterated sumset, NA, equals 12n minus 6 for all n. The Khovanskii threshold is 1. However, because of how I've cooked up this example, the structural threshold turns out to be 2 because of the element 6, which is non-exceptional, yet you need to add 3 to itself twice to construct 6. Okay, so this example was constructed after some serious fiddling about to make the intersection between exceptional sets marry up with some other additive property elsewhere in the sets. And it's an open problem to classify such examples. They seem to be rather special, but maybe they're not. Maybe there's a whole zoo of these examples out there for which, in fact, the moral of how we feel the situation should behave just doesn't hold. Okay, so that's a question I'd very much like to see answered. Okay, so we're leaving dimension 1 now. So if you have any more questions about the one-dimensional case, now's the time.
I just have perhaps another silly question. Lower bounds are easy to obtain for these numbers.
So in explicit cases, completely, because in explicit cases you can identify non-exceptional elements just by some calculation, and then you can see how many iterations you would have to make in order to represent them. That is, broadly speaking, what we did with this set 0, 1, b minus 1b. However, to get some general lower bounds in terms of some other properties of the set A, I think that could be extremely difficult, because I think you could end up running into the fact that it's quite hard to calculate the exceptional elements for a set A. That's a computationally complex problem. And so getting some lower bound that worked for all sets would require you to get some general lower bound on what these exceptional elements look like. Maybe that could be done. I haven't thought about it.
Okay, thank you.
Okay, so I'm enormously over time about where I wanted to do. I think probably what I'm going to do is, you'll be glad to know, most of these slides up here in structure are sketching a proof that I'll omit. So I'll omit that at the relevant points and get on to the end of the talk. So let's talk about the second aim, which is about higher dimensional structure, generalizing Nathanson's results at higher D. So it turns out that there is, I feel, a very natural way of doing this that was introduced by Granville and Shakan. It requires a bit of notation to set up, but I'll be drawing loads of pictures, and the pictures, I think, are very self-evident about what's going on. So the general setup A is in Z to the D, and rather than the interval between 0 and the maximum element B being the critical object, now the convex hull of A is the generalization of this, the general D. So H of A will be the convex hull of A. We'll translate things so that the origin is a corner of this convex hull. It's an extremal element of the convex hull. That's what we did in one dimension, right? We translated things about so that 0 was the minimum element of A. And this is just the same. And finally, the analog of assuming that the GCD of all the elements of A is 1 is assuming that the lattice generated by A is the full integer lattice, Z to the D, rather than some proper sublattice. Okay, so these are going to be our 4 assumptions about the set A. Now, in one dimension, the positive reals played a role. We didn't really think about it, but all of the action took place within the positive reals. All our sums, they were all in the positive ray from 0. So in higher dimensions, there's a similar role played by the cone generated by A, the set of all non-negative linear combinations of A, real linear combinations. There'll be a picture coming up in 30 seconds in which I'll describe all these things. So the semigroup generated by A, of course, it's integer lattice points, and it's all contained within the cone. But maybe it's not the entirety of this set. Okay. In the same way that the semigroup generated by A in one dimension had some exceptional elements, there's going to be some exceptional elements in this case, namely those elements in the real quadrant that A generated that are not in the semigroup generated by A. So these are our exceptional set. Time for a picture. Okay, so this is the picture that I hope we'll get things clarified. This is a picture for D equals 2. And it's about the 4-element set comprising the origin, 2, 0, 1, 1, and 0, 3. So that's the set A in red. In black, I've put the semigroup generated by A, this union of all the sumsets NA. The cone in this case is just the positive real quadrant, right? That's all the elements you can get by positive real linear combinations of A. And you notice that there are some elements left over. There's no way you can add elements from A to get the point 2, 1. There's just no way of doing it. But similarly, you can't get 2, 4. Nor can you get 2, 7, nor 2, 10, and so on. In fact, there are these arithmetic progressions of exceptional elements. This diagram is repeated here. So the exceptional set is in fact a union of 8 one-dimensional arithmetic progressions that kind of hug the boundary of the cone. This is in some analogy with what happens in one dimension, right? The exceptional set is finite. It hugs the boundary of the cone. The boundary of the cone is just the origin in one dimension, because the cone is the positive real line. But in higher dimensions, the exceptional set is infinite. So this is already an extra complication about what's going on in high dimensions. Okay, so what does structure look like here? Well, in one dimension, remember we had this inclusion. This was our complicated expression. NA was included in this interval set minus these exceptional sets. The generalization of this is as follows. For all D and for all n at least 1, the iterated sumset NA is a subset of the dilated convex hull, intersect the integer lattice, removed all the exceptional elements suitably translated by the corners of the convex hull. And the argument for this is the identical proof as for one dimension. So I put these next to each other to show the direct analogy. In one dimension, the corners of the convex hull are just 0 and the maximum element. So there are just 2 exceptional sets to remove, one near one corner and one near the other corner. But in higher dimensions, you need to remove something for each corner, and there could in general be many more corners. So the structural threshold is the minimum n such that equality holds. And of course, the hope is that if you understood this structural threshold really well, you'd be able to understand the threshold in Khovanskii's theorem very well. That's the reason for introducing this notion. I'll get to that at the very end of the talk. So, basic question, it's far from clear that this threshold exists. Maybe you never get equality for any n, because these exceptional sets are infinite now, right? It could be that every non-exceptional element is eventually represented. That's true by definition. But maybe for every fixed n, you're always going to find some non-exceptional element that misses from nn. I think it's not a priori clear that that doesn't happen. However, my co-authors proved in 2020 that this structure threshold exists by a cunning argument that gave a completely inexplicit bound. So it's very good in our hearts to know it exists, but it doesn't actually necessarily help you for any particular set. Why was their result inexplicit? Well, it relied on a small little lemma about lattices that goes by different names, and one of the names is called Dixon's lemma. So I have a formal statement at the bottom of this slide, but I think the picture is far more explanatory, so I'll just skip towards the picture about what Dixon's lemma tells you. Dixon's lemma is about the following picture. So this is in 2 dimensions. The set S is all the blue shaded region of integer lattice points. And the content of Dixon's lemma is that there are finitely many corners to this set. Finitely many black points, which are denoted T, such that all the elements of S lie above and to the right of some corner, some black point T. And Dixon's lemma says there are only finitely many points T, and maybe you can just believe that by picture. If I have some zigzaggy line, there's only going to be finitely many corners. But it's ineffective. The proof does some induction on dimension, reduces to the well-ordering principle, but it doesn't give you any handle on what properties of S you're looking for in order to bound this T. And in particular, that ineffectivity influenced the ineffectivity in the structural threshold. So, just building up to stating our main results on this, explicit results were known in a few special cases. In particular, when the convex hull of A was a simplex, so a triangle in 2 dimensions or a tetrahedron in 3 dimensions and so on. So in general, the convex hull being the origin contained with d other points, which form a basis of R to the d. So Michael Curran and Leo Goldmacher, Curran is currently a PhD student at the University of Oxford, they made the non-trivial observation that this case was tractable. So now once you made that observation, it's somewhat clear what you should do, but it's very, very not obvious that this is the right setting to look at for an easy argument. So they showed that if the convex hull is a d-simplex, then both of these thresholds are bounded above by d plus 1 factorial times the volume of this convex hull minus 2d minus 2. Okay, and I had actually one other result. This is not tight for d equals 1. You get 2b minus 4. I told you that you get something that's just b minus the size of a plus 1. That's my result with Andrew. But still, it's linear in b, so it's not so bad. They also had some results for sets of size d plus 2, but I won't go into that. So before I state our results on this, what should you conjecture to be true? Well, we've got examples where the main term is d factorial times the volume of this convex hull. That corresponds in 1 dimension, let's go back to 1 dimension that we understand, to the main term being b. Right, so that's the thing that in my paper with Andrew Granville we established was the main term. And so we've been motivated to conjecture that both these thresholds should be bounded above by d factorial times the volume of the convex hull minus the size of A plus some constant depending on d. So we made this conjecture, and then we realized that this conjecture already existed in a completely different part of mathematics. It is an instance of the Eisenberg-Goto regularity conjecture in commutative algebra. And so what I'll do in really my final few minutes, if you permit me to go a couple of minutes over time, I'm going to sketch or explain very roughly why commutative algebra comes in, and this is still quite a nascent part of discovery in this project about why these things are related. Okay, so this is what you should try and prove, but at the moment, at least in this talk, we only have explicit results in very special cases. And the final thing I'll say before I move on, when d is 1, of course the convex hull is always a simplex. The convex hull is just a closed interval. And so you don't see the subtlety when d equals 1. You only see the subtlety for higher d, when in fact the geometry of this convex hull really influences this antitocombinatorics and how easy or hard it is to do things. So, having built up for 45 minutes or whatever of chatting, here's the result that we proved. Well, it first appeared a couple of years ago, since refined slightly. We showed that for an arbitrary set of z to the d, you can upper bound the structural threshold by something explicit, and maybe non-terrible, like it's something involving something we call the width of A, namely the maximum L infinity norm of the difference between A1 and A2, and some exponent that depends only on D. Okay, so this was our result, and I think I'll say 15 seconds about why the one-dimensional techniques don't work. The one-dimensional techniques utilize the fact that if you have a sum that's in the cone generated by A, that's congruent to 0 modulo B, it's a positive combination of these, because everything's happening in the positive reals. In higher dimensions, this need not be the case, because the geometry can be more complicated. You can be congruent to 0 modulo a lattice, but not in the cone generated by that lattice. And this is a fundamental issue that means that all these basic combinatorial methods fail. Okay, so we have a more complicated technique, which I will not discuss. You can see some pretty pictures that you can ask me about later. So let me close the talk by talking about size. And in fact, even I'll skip the simplex case and go to the general case. So before our work, there was no explicit threshold known for this Khovanskii threshold for general A. And so in 2021, we proved the first general bound. Again, it's a similar shape to our structural bound, albeit with entirely different methods. But note the exponent now depends on the size of A as well. This is because it's proved by some linear algebra techniques that exist not over R to the D, but over R to the size of A. That's why the size of A occurs in the exponent. Okay, but I promised updates. Okay, we did some careful quantitative linear algebra around the Nathanson and Ruzsa proof. I promised some updates, so here's an update. We've seen a much slicker version of this proof, which greatly improves the result. So in fact, notice it gets within the size of A squared of our conjectured upper bound. How did we do this? We did this by realizing that there was lots of work in the commutative algebra literature that was relevant to us. In particular, work of Sternfels on toric ideals and toric varieties. So I think I'm going to put the next slide up and then close the talk. Okay, so how much this makes sense will depend on how much you remember your undergrad or maybe first year grad school commutative algebra. If you have a graded module over a polynomial ring, you have some homogeneous parts which have, according to degree 1, 2, 3, and so on. Now, these are, say, vector spaces over C, if you're dealing with polynomial rings over C, and so they've got a dimension. And it was a famous theorem of Hilbert from 1890 that there is some fixed polynomial, which is called now the Hilbert polynomial, which agrees with these dimensions once the degree is large enough. So let's say once you look at degree 100 pieces and above, you can read off the dimension from this polynomial. And it was Khovanskii's great insight that you could apply this theorem in the context of algebra combinatorics. You could construct some graded module for which the size of the iterated sumset was exactly the dimension of the homogeneous pieces. Now, Khovanskii didn't do this in quite this way, but I can just write down for you what this module is. And for those of you who know the Nathanson and Ruzsa paper, this may look a bit familiar. It's just a quotient module from a polynomial ring where you quotient out by binomials which somehow respect where you get coincidences in the sumset of A. This is what it is. But so this leaves open to you lots of techniques from quantitative linear algebra. And in particular, Sternfels wrote a whole monograph about the particular kind of ideals, so-called toric ideals of this case, and something called the Castelnuovo-Mumford regularity of these toric ideals. And so although you have to do a bit of translation from that commutative algebra language into an additive combinatorial language and do a few slight tweaks, there are some very strong linear algebraic ideas that you can. So I think I'm going to stop there. I'll mention that the write-up we have of this, it's not on the archive yet, but it's just in terms of the language of linear algebra. So we've excised the Grosvenor bases and other such things that come in Sternfels' treatment. But of course, the holy grail would be to combine these techniques we have, the Khovanskii threshold, and the techniques we have for the structural threshold. we're just starting to be able to do this. There was one result I had to skip over in the slides where we have some improvements by this idea, but the story is still far from over. Okay, so that's the end of my update on sumset stability, and I should stop there.
Thank you very much, Aled. It's a beautiful talk. Very nice. And now we have time for questions. Does anyone has a question to Aled?
I do. Olivier. Yes?
Yeah, go ahead.
You have your set A, and do you have any how stable are the results if you modify A by some unimodular matrix? Do you have any idea?
So let me think. So although for simplicity's sake, we chose not to express the results this way, we have some kind of footnotes where if you apply any prime and isomorphism of all orders to A, of course you should get the same results. So if you just look at the statement of the theorem, the bounds, at least in our first paper, are not symmetric in such transformations. No, of course, the setup is symmetric in that transformation. So if one was so minded, one could write an updated version of the theorem where you take the minimum overall unimodular transformations of A. It's the business to do this width of A. We found it just convenient to bound A within some large box. And of course, a large box is not preserved under such transformations. This is one of the advantages of these newer approaches, because of course the volume of the convex hull of A is preserved under such volume preserving transformations. So those bounds are completely symmetric. If you'll permit me to go back a slide. Now, of course, this bound here is preserved under all such transformations that you talk about.
Yeah, thank you. It's convex analysis and integer point, and they don't go well with this transformation. Thank you.
Okay. Anyone more has a question?
Just should be another question. Do you have an idea of the exceptional set in dimension 3?
Well, so we know that it hugs the boundary of the cone.
Okay.
And we have some orbit, I think, very weak bounds on how much it hugs the boundary. Like, so we have some distance from the boundary within which the exceptional set is contained. That's one of the partial results that we need to establish in order to get our whole theorem to go through. And we also know it's the union of arithmetic progressions of dimension 1 lower, or dimension 2 in this case. But in terms of, what is the common difference of those progressions? How large are they when you stop? I think these are very subtle questions, and we didn't try to address them.
Okay.
Perhaps one thing I should mention, just in case anyone thinking of a final question, has been evidence from my perhaps inability to fully answer several questions in this talk. There are loads of side avenues that for one reason or another we haven't chose to focus on, but I think it's a very rich area. And so I think it's a good kind of area for student projects or whatever. There's lots of unexplored territory here. So that's my marketing pitch at the end of the talk.
Mm-hmm. Okay, more questions? If not, thank you very much again, Aled, for the talk. So I will stop recording now.